All right, so we're moving on to the 31st problem in the grind 75. This one is called binary tree level order traversal. We're given 20 minutes, so let's pull up the timer tab and let's start the 20-minute countdown now. Okay. So, given the root of a binary tree, return the level order traversal of its nodes values. Okay, from left to right, level by level. All right. Okay, level order traversal. So we just have to figure out how to do this, and this is what we want to output. So we have a list. Each sublist represents each level. So the first sublist is going to represent the first level, second sublist is going to represent the second level, and then we just go left to right. Let's see. So here are, they're nice enough to give us some base cases. We should also take note of the constraints. Yeah, so values can be some integer, nodes can be 0 through 2000. So it's a binary tree, it doesn't necessarily have to be balanced, but that's okay. So let's see, how would we do this? Can we do this iteratively? I mean, I'm sure there's a way to do it iteratively, but recursion seems to be the best way to go. So say we go down left and then right. We have to have some way, say, I'm gonna actually draw really quick. Not really going to pay attention to what the node values are. What I really want to pay attention to is the structure of the tree. So we're going to switch over to paint, and let's pick our favorite color. I'm going to use the tree that was in the example. So 3, 9, 20, 5, 17. So something like 3, 9, 20, 5, 17. The values seem to be pretty arbitrary, so I'm just going to say we're not really looking for the values right now. We're just looking for the structure of the tree, as we said. Okay, so we obviously start off at the root. Base case, if we have a empty tree or a leaf. So I'll just note that really fast. I'm going to switch back over. So base case, empty tree, or just leaf. Let's see. So going back to paint. Okay, so we can start up here, and we want to get our current levels, everything there, right? But I think this would be sort of a better example once we're down there. Since we can only be on one node at a time, we can obviously get this node's children, but then how do we put it into the same list as this node's children? So let's see. So one method we're going to be using is called arrays.asList. Let me just make note of that also so we don't forget. Gotta switch over. Arrays.asList. So that way we can pass in an arbitrary number of arguments, and it will just load into our list. So again, how do we maintain a level? So say we're starting up at the top. First off, we have to make a list and then a sublist. So we're going to have a overarching result list, which I will type up really quick, and then we're going to be creating sublists as we go. So we're going to say array list, or actually this is going to be list of list type integer. Result is going to be equal to new array list. We're not going to specify what's in here, but we know that we're going to be adding list objects or array objects. And let me actually switch over just so we can see. This is what we did. So we're at the root. Say we want to look at our, so we have access to left and right as per, yes, left and right, because this is a binary tree. So basically we can say, so we're going to create a new array and add our root, and then we're going to say maybe arrays.asList recursive call on left child, recursive call on right child. So we have to be careful of what order we make the node's actual arrays. So let's see. How do we push these together? Once we're on a specific node, we don't know how many, I guess, siblings there are, how many people on the same, or how many nodes on the same level there are. So all we can do is really make an array out of ourselves. Or do we have to? We just make an array. What if we just make an array out of the recursive call? So once we're here, we say arrays.asList, recursive call on left and recursive call on right. So that would be the top-down approach. There's also bottom-up. Not really sure which one works better for this particular problem. We could have some sort of count for the level that we're on. And that seems sort of unnecessary. I'm sure there's a clearer way of doing it. That would take up extra memory, but we'd still be traversing the tree normally. So something we could do is yeah, that might work. So what I'm thinking of, which I'm sure there's, as I said, a better way of doing this. I'm going to switch over to the LeetCode window just so we can see the notes. So as we go down, so we're going to take a top-down approach. So we're going to create separate function that keeps track of level, and we're going to add nodes of same level to, so I guess what we're really going to have is a hash map where the key is going to be the level, the value is going to be a linked list of nodes on that level. Let's see. However, we do want to go in level order traversal. So will this not work? So we will, thinking back to the example where we had these 4 children here, because we're making the left because we're making the left recursive calls first, we're going to hit this left one first. And then we should go right. Yeah, so this should yield level order, I believe. Okay, and then in the end, we will iterate through the hash map, grab each linked list, and just load it into our result. And that should be that, actually. Okay, let's try to implement that really quick. I'm going to switch back to the LeetCode window. So let's see. We're going to create a hash map. It is going to have a key of integer, which is going to represent the level, and a value of linked lists, which maybe we'll just say list. And this one is going to be called, I'll say level builder. It's going to be equal to a new hash map. We'll say it's this for now. Linked list. Maybe you type integer. We don't really have to specify this right now, but so let's see. So we will have to traverse through the whole tree. So we are going to make a separate function that's going to do the addition. So we're going to say private, this is going to return nothing. I'm going to say build level. And that's going to take in tree node, we're just going to call it root, and then it's going to take in the level that we are on. And we just have to think, since we're essentially counting height, right? So okay, so private void build level tree node level. So what do we need to say? As we're, so we need to check left and right, and we need to go down there. So okay, so if root is equal to null, then what are we going? We're just going to return, not going to return anything. However, we're going to say else if we've reached a leaf. So else if root dot left is equal to null, and roots.right is equal to null. If that's the case, we know we're at a leaf, and we will want to add that to our level builder map. So what we're going to do is say level builder, which we're going to make this public so we can access it outside of this function. So I'm going to make this public up here, or global. Do that. We're going to say level builder dot add, and we're going to add the level and the roots value. Right, okay, and if that's not the case, then first we're going to recurse down left, which we don't have to actually return anything. We can just say build level root dot left count is going to be equal to level plus 1, or I mean, we're going to increment the level, and then level build level. I'm going to do root dot right level plus 1, just like so. And 1 second. So we have this. We're adding to the appropriate spot. We should pass in level build.add. Okay. The first thing we have to do is pass in level builder, or what are we going to do? We need to call this function build level on our root. So we're going to say root. We're going to start off at level 0, right? And we can say now we're going to load it into our result, and we're going to say for int I initialize to 0, while it's true that level builder dot contains key I, while that's the case, we're going to increment I. We are going to say result dot add level builder dot get, and we're going to pass in the level that we are on. Level builder is a linked list. That's correct. Yes. Okay, so that should be simple enough. And in the end, all we have to return is result. And I believe this should work, actually, unless there is some missing, what would we be? Just some syntax issues. So let's run really quick. Okay. So level builder.add in here. So I'm just going to start off by just going to call this list, like so. Level builder.add, method add, root val. Okay, so we simplified it a little bit too much. What we have to do is first check if level builder dot contains root dot val. Well, if it does not contain root dot val, then we're going to have to create, in our case, we're going to make it a linked list. The timer, but we're very close to being finished, so I'm just going to round it out really quick. So if level builder does not contain our current level, actually does not contain our level, then what we're going to do is say list of, I'm going to say list new level is equal to linked list of integer, initialize that, then we're going to say level builder.add level and root val. And we can just say maybe integer here. Okay, so let's run really quick. I have to say new. I like to forget that. Okay, cannot find symbol. Dot contains what? Contains key. Add cannot find symbol. Yeah. So, okay, yeah, again, oversimplified. We're gonna have to say linked list integer my level is going to be equal to that, and we're going to say my level dot add. We're going to add in our value, so root dot val, and then we're going to put it back, which we don't actually have to put it back into the hash map because we're taking a pointer, pointing it to the actual object that's in that value position, and we're just adding to that object, so we don't have to reinsert. So this should be good. So let's just run. Okay, what do we have? List cannot be converted to linked list integer. Then I'll just say linked list integer. Okay, so our static types will be interfaces. Our dynamic types, okay, cannot because object is null. Okay, we're having a couple issues. So okay, I'm going to stop the video here. I might work out some of the smaller things on my own, but I believe this is a working solution, but I'm almost certain there's a much cleaner way of doing this without using as much memory and data structures for that matter.